All right. Hey, folks, how we doing today? Well, we get our second to last video for AP Calculus, and we are done with AV for the year. So, um, this next little bit, we talked last time about um, regions being bounded and find the area in between them. Well, what happens if we take those areas, those regions that are bounded, and we start to revolve them or rotate them? So we're going to talk about taking a region that's bounded. So let's just put a graph up here. All right. I did not want that to be that color. Let's try that one more time here. There we go. All right. So we have ourselves a region. And we're going to call it some function. We'll call it R of X. And you'll see why the letter R here in a second. And what we're going to do is we're going to take this function, we're going to revolve it around the x-axis. Now, I can also revolve a function around any vertical line as well. It doesn't have to be a horizontal line. Now, I want you to imagine, what if we were to be looking straight on this from over here off to the side, looking straight at that function? If we were to be looking straight at that function, what we'd probably see is just a vertical line. Now, if I take that vertical line and I rotate it 360 degrees, we'd say that vertical line is some R value. And when we rotate it, it would look like a circle. So that R value, looking straight on, we're looking straight at the end of that function. That R value, if I wanted to find the area that was created, well, that'd just be the R value times pi, where we'd square the R value, because we'd end up getting some area. Well, in this case now, when we take ourselves and we go from looking directly on it and look at more at it from a side, that R value is not just a number, a length, it's actually a function. But we're going to do the same thing. Instead of taking a length or a number and squaring it, we're going to take a function and we are going to square it. So when we take that function, we're going to square it. So now we have that function times pi r squared. Let me put that in a different color so it's a little bit easier to see. And when we do that, when we rotate that function, we end up creating a volume of some solid, some three-dimensional solid. This is called rotational volume because we're rotating it around some axis. Now, like I said before, we could rotate it around a horizontal axis. Or we could rotate it around a vertical axis. Horizontal, or a vertical axis. So if we were to take it and go around a horizontal axis, always fun to make little car sounds as you're doing your math, friends. I'm not going to lie. Makes it a bit more enjoyable. So let's go ahead and add this here. If we were to go around our horizontal axis, we would have to have some lower bound. We'll call that A, just like before, and an upper bound. So it's like we're finding the area of our solid, find the area between these things, but then we're going to use that area in our equation of a circle. So this is around some horizontal axis. So right now, if I'm rotating around there, I'd be rotating around the x-axis, right? The x-axis, remember, is y equals 0. But any horizontal axis is y equals some k value. So the volume then would have been, and we're going to add to this a little bit as we go. So I'm going to take whatever that is. I'm going to find whatever that function is, I'm going to find the area of it, but I'm going to square that area, and outside I'm going to multiply by pi. So again, we have pi r squared, pi r, or the function, squared. And if I'm going around the vertical line, remember that if I were to go around a vertical line, the y-axis is the vertical line x equals 0. So we have A, and we got B here. And any axis that's a vertical line is going to be some x value, x equals h. In this case, it would be x equals 0 if it was the y-axis. And again, it's the same thing. It's just instead of doing it towards dx, we're going to be using dy. So we have our function, our volume function for a vertical thing, a vertical area. So this idea of rotating it, this is what we call the disk method. So this is our first method that we're going to be looking at. It's called the disk method. Eventually, we're going to have two disks going at the same time, and we call that the washer method. So this is the disk method. So we're going to play around with this a little bit here and see what we can deal with. So say I give you an equation. Say, determine the volume of the solid, let's try this, of the bounded region by y equals the square root of x minus 1. I'll come back and put that in square root here in a second. And the x-axis from x equals 1 to x equals 5. So in other words, I'm not going to draw all these out. I think you guys are going to be able to draw most of them here. So we're going to go from 1 to 5. 2, 3, 4, 5. So what we're saying is we're going to take the function here from 1 to 5, and we are going to rotate it around the line, around that line, y equals 0, or the x-axis. So if I take my horizontal volume for this, I'd have pi times, let's see here, I'm going to go from 1 to 5. And then I'm going to take that function, I'm going to put it in side, I'm going to make that my r of x function, and I'm going to square it. So notice, down here we have some function that we square. Well, that function is the function that we are actually revolving. So if I wanted to actually go ahead and solve it, wouldn't be too terribly bad. I'm going to take pi. And I'm going to go from 1 to 5. So after I square that function, I end up with x minus 1, because the square and the square root cancel out. So we have 1/2 x squared minus x. We're going to evaluate it from 1 to 5. So we plug it in there, friends, and we end up, keep that pi on the outside, no reason to move it inside. And we have 25 halves minus 5. And then we're going to subtract the lower bound, so 1/2 minus 1. And altogether, that would be 8 pi. And again, that's what we'd get if we went around the horizontal axis, the x-axis. Let's see if we can't make it go around the y-axis. So after I write this one out there, why don't you guys go and pause the video and give it a shot. We'll use the same function here. From y equals 0 to y equals 3. Let's try that. All right. Be careful, because notice, look at the equation I gave you. Try to figure out what you're going to do with that. All right, give it a shot. We'll talk here in a second. All righty, friends. Let's see how you guys did there. So to begin with, notice I have y equals x minus 1. But if I'm going to rotate around the y-axis, I'm going to have to change my function and make it in terms of x. So I'm going to take my y equals the square root of x minus 1. Whoop. There we are. And I'm going to have to solve this for x. So y squared plus 1 equals x. Now, from there, we're going to use our disk method here. So I'm going to go from 0 to 3. Those are my bounds. And I'm going to take this function I found, y squared plus 1. I'm going to use that as my function. So I'm going to square it. Notice how I have the pi outside. So again, it's pi r squared. All right, so to integrate this one here, I'm going to have to go a little bit further out here. I'm going to have to multiply this all the way out. 0 to 3. We have y to the 4th plus 2y squared plus 1 dy, and now we can integrate and solve. So 1/5 y to the 5th plus 2/3 y cubed plus y, and we're going to evaluate that from 0 to 3. So plug in all my numbers here. So 3, that'd be 243 over 5. Y cubed, 27 times 2, that'd be 54. So plus 54/3 plus 3. And I'm going to subtract. But, well, if I plug 0 in for all those, that's just 0. So that makes it easy. So on the FRQ, I would actually stop there. Actually, I would have just put the 3 in for y and not even go that far. But if it's not on the FRQ, we got to go a little bit further. If it's on a multiple choice, well, they're going to want to actually know the answers. 348 fifths times pi. All right, so this is that idea of revolving. We're revolving it around the x-axis, and you can kind of see here, if we would have gone from 1 to 3 here, if we would have revolved it around the y-axis like we did, that's just pretty much taking this whole area and rotating it all the way around. So here's what we got so far. And I'm going to do this with respect to the x-axis. Let's see here. No, we don't want to do that. Let's do a straight line. And we're going to try to see if we can see this here a little bit. Because so far we've been doing the x-axis and the y-axis, but it doesn't always have to be the x-axis and the y-axis. For instance, to begin with, say our axis is that x-axis that we're rotating around. If that's the case, here's our function, whoop, and I'm rotating around there. If that's the case, then our volume would be pi times a to b, or from a to b, r of x squared. Okay, and that's what we just did. That does not look like a 2, does it? There we go. And so that's taking this area right here underneath that and the x-axis, but more, not necessarily the x-axis, but more the y equals 0, our axis that we're revolving around. And it's taking it and spinning it 360 degrees. But what if we were to take that axis and move it so that it is further below? And say we're going to revolve it around that axis. We also could take our axis and move it above. And we could rotate it around an axis that's above it. So if I were to take my function there, notice it's going to take that area and it's going to make it a lot bigger than what I had before, because it's no longer stopping at the x-axis. The area I'd be revolving around would be all the way down to whatever it is that the axis I'm revolving around. It just made the volume that much bigger. If the axis is above it, then look at my volume. The volume I'm revolving around doesn't go to the x-axis, it would go to the axis itself. So when we start changing our axis of revolution, we have to start thinking about what's bigger, what's on top. Is our function on top of the axis, or is the axis on top of our function? If the function is on top of the axis, for our disk method, we'd have r of x minus the axis squared. If the axis is bigger, then we're going to take the axis. We're going to always start with the greater value, which is either the function or the axis, and we're going to subtract the smaller value from it. So let's try a couple of these here and see what we can do with this as we go a little bit further. You guys have been spoiled. We've had really short videos for a while. Now we're going to get a little bit of a longer one. Determine the volume of the region bounded from y equals 2x plus 1 from x equals 1 to x equals 4 when the region and the given axis of revolution. So our first axis we're going to revolve around is going to be y equals 3. The second one we're going to revolve around is y equals 9. So I'm going to draw it out for you real quick. I kind of want you to see what it looks like. All right, so we have ourselves our y-axis, we have our x-axis, we have 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So what we're saying is if we graph this function, when x is 1, y is 3, and then we have 4, 9. So we're going to take this function and we're going to first revolve it around the line x equals 3. So notice for this one, our volume is going to be coming down. Our second one we're going to revolve it around the line y equals 9. Notice the axis is on top of the function. On the first one, y equals 3, the axis is below the function. But on the second one, y equals 9, the axis is above the function. So on the second one, we're going to spin that volume. So what does this look like? On the first one, the function is greater than the axis. So our volume would be pi. Whoop. We're going from 1 to 4. But I'm going to take my function and I'm going to subtract my axis. On the second one, the axis is bigger. So I would take my axis and subtract the function. So we don't have to just revolve it around the x and y axis. We can revolve it around any vertical or horizontal axis we want. That should have been a 9, not a 3 right there. Oops, undo. There we go. So we'll go ahead and do this real quick. So we have to clean up the expression first. So we end up with, from 1 to 4, 2x minus 4 squared. And I could do a u substitution there if I wanted to. I don't want to. I'm going to go ahead and multiply it out. And I end up with 4x squared minus 16x oopsies. That should have been a plus there, shouldn't it? Oopsies. That would have made that a 2. And when we square that, minus 8x, there we go, plus 4. So the volume, after I integrate it, I'm going to end up with 4/3 x cubed minus 4x squared plus 4x from 1 to 4. And that would end up being 36 pi. If we did with this one over here, we would end up with, oh, what would that be? 8 minus 2x. And again, I would go ahead and I would multiply this whole thing out. So 64 minus 32x plus 4x squared dx. And then we integrate it. Notice we're bringing that pi with us the entire time. One of the biggest things people miss is just that pi. They forget to bring pi with them. And friends, I'm not gonna lie, I dig a good pie. I am so sad that we won't be able to enjoy Pi Day together, but it is what it is. No harm, no foul. From 1 to 4. And that would end up being 36 pi. So we have this idea of a horizontal rotation. And when we're dealing with this here, friends, we're basically saying we have when we're saying function minus axis, what we're basically saying is that the function is greater than the axis. Axis minus function, that means the axis is on top of the function itself. So what happens if we go vertical with it? I bring out magic eraser here. Everybody loves good magic eraser. I tell you what. Save from having to write all that over again. Whoop. When we say greater function when we're dealing with vertical, what we're basically saying is what is further right? So further in the positive direction. So if I was going around a vertical axis, say I have an axis like this, if I'm rotating it around there, so we'll just go ahead and draw the whole thing back up again. And then we have our vertical axis over here. Well, if we're going around the vertical value, we still have A to B. It's just now we're saying all the way, which one is more further right? That'll be the greater axis or the greater value. So if the function is more right, it'll be function minus axis. If the axis is more right, then it would be axis minus function. Wrong color. There we go. So this would be V of equals pi from A to B. And again, everything is the exact same. It's just instead of R of X, we'd be using R of Y. When we're dealing with the disk method, we have to always ask ourselves, what's greater? And if the axis was bigger, it would be axis minus the function. So let's try one of those. Oh, determine the volume of the region bounded. Oh, let's see. Let's go. Region bounded around y or x equals -1 and y equals x cubed when the from 0 to 3 when the region is rotated around the around x equals -1. So we have a vertical rotation. So we're going to rotate it around a vertical line. All right. So actually, this should be a horizontal. So we're rotating around a horizontal line here. And right here, we are rotating around a vertical line. But if it's around a horizontal line, it's technically a vertical rotation. Let's see, can't add that one in here. Okay, so we have this line. Let's go ahead and graph it so we can kind of see what it is we're looking for. Now, notice I didn't give you two different problems. I'm only going to ask you to do one. We've already kind of got the gist of how this whole thing is working. So here's the line x equals -1. So I'm going to rotate around that. And the line y equals x cubed. So that would start here. I'm going from 0 to 3. So that would go from here to here. Okay, so 0 to 3. And we're going to rotate that around the vertical line. So in other words, this value right here is going to get rotated all over the place. Now, since it's the function is to the right of the line of symmetry, I'm going to go function minus the axis of symmetry. Now, if the axis of symmetry was further right, I'd go axis minus function. So it's just a matter of just trying to determine what order you're dealing with here. I do have one issue though. My equation is y equals x cubed. I need that to be in terms of y. So y equals x cubed is the same thing as the cube root of y equals x. Or in other words, y to the 1/3 equals x. So that means my volume, I'm going to go from 0 to 3. The function is bigger, so that comes first. So y to the 1/3 minus my axis. My axis is x equals -1, so y minus -1. And then I'm going to square it. Oh, forgot my pi. All right. So we're going to go ahead and multiply this whole thing out here. So that's the same thing as y plus 1. So when I multiply it out, I'm going to end up with y to the 2/3 minus plus 2 y to the 1/3 plus 1 dy. So we integrate it, whoop, and we end up with 3/5 y to the 5/3 plus 6/4 or 3/2 y to the 4/3 plus y, and we're going to evaluate that from 0 to 3. And when you do that, friends, you end up with a really hugely ugly decimal. So you end up with, or fraction, you have 45,023. all over 3,402 pi. That's one of these where you would probably just go ahead and get your approximate decimal answer, 13.2343 pi. Okay, so we have our disk method. Biggest question we always ask ourselves, or two of them, are we rotating around a vertical line or horizontal line? And the next thing is, what's greater, the function or the axis, as that will determine the order that we write it when we do our subtraction. Now, sometimes we have two functions, and this will get us to our final thing today. Sometimes we have two functions that we are going to be rotating. And we're going to find the region bounded by two functions. So if we're getting rid of a region bounded by two functions, that's called the washer method. So let's take a look at two functions here. Let's take the function y equals x squared, and we'll try to use this to help us figure this whole thing out here. Y equals x squared. And how about the line or the function y equals the cube root of x? What if I wanted to rotate that around the x-axis? In other words, I'm just going to take this region right here and rotate it all the way around. Well, there's two ways to do it. The first way is to do essentially a combination of two disk methods. Now, in order for us to do that, let's go ahead and figure out real quickly where these bounds are so we have an idea. So in order to figure out where the bounds are, I do need to set the two things equal to each other. So the cube root of x equals x squared. Cube both sides, I get x equals x to the 6. So 0 is x to the 6 minus x. So we have x factored out. We have x to the 5th minus 1. Therefore, x equals 0 and x equals 1. So it's going to be bounded between 0 and 1. So the first way we could actually do this is we could take the region that is furthest away from my axis and subtract the volume that is closest to my axis. So if I'm looking at it, the one that's furthest away is the red function. So one way to do this is to take the red function, take that volume, oopsies, don't know what I was thinking on that one. There we go. So we have the cube root of x squared and subtract the volume of this, or the smaller volume. So the one that is closest to the line I'm revolving around will be the smaller volume because it's got less to travel. So that'd be x squared. So we could do this essentially as one volume cut out of another one, or we can use something called the washer method. And the washer method is basically taking the two disk methods and putting them together. And we'll formalize this here in a second, but let's just talk about what the washer method would actually do. Washer method basically says, hey, let's just do one big gigantic function. So big function, so x to the 1/3 squared minus the smaller function, x squared. And then just do them both at the same time. So really the washer method is two disk methods just thrown together. And if we were to do that, then friends, we would end up with, and we'll go ahead and figure this one out real quick. So 0 to 1, we end up with x to the 2/3 minus x to the 4th. And then we're going to integrate. So 3/5 x to the 5/3 minus 1/5 x to the 5th. And we're going to evaluate that from 0 to 1. So our volume would be 2/5 pi. So a washer method, or this washer method, is really trying to determine what comes first, or what's the bigger volume. In other words, the way we figure that out is what's furthest away from our axis. So a washer method is basically taking two disk methods and putting them together. So if we formalize that, here we go. The vertical rotation around a horizontal line for washer method. Whoop. All right, so in this one, what we need to remember here on my values I'm using here is that f of x is going to be, I'm going to say that f of x is the function that's furthest away from the axis. G of x is the function closest to the axis. So we have a couple things that could happen here. If the functions are greater than the axis. Or we could have the axis is greater than the functions. That would be the volume equals pi. So we're just taking that same idea that we did before with the disk method, but we're going to actually have two disks as part of this same problem. So f of x minus the axis. So there's the disk method. And I'm going to subtract the smaller one. And if the axis is on top of the functions, this would be going the axis first. Again, taking two disk methods and putting them together. And f of x is the function that is furthest away from the axis. Now, realize, whatever the greater function is, when the axis is below the region, they'll flip-flop when the axis is above the region. We'll see an example of that here in a second. But just so we're aware of that, that will happen. And likewise, we also have our horizontal rotation. For the washer method. And when we're saying greater than here, in this case, greater than means which one is further right? we have oops, wrong color. And then we'll do one problem, and then we will call it a day. Functions greater than axis. Notice the axis doesn't run through the functions. That would be a very bad thing, right? So it's either the bounded region is going to be more right than the functions, or the axis will be further right than the bounded region. So we're just going to take our x's and we are just going to change them to y. So a, b, f of y minus our axis. So that's our first disk. And we're going to subtract our second disk, one that is closest to the axis, because that would have the smaller volume. So we get our full washer method out here. And notice each of one of these, they just kind of build off each other, right? We had the disk method that's going either at the x or the y axis. And that really was the disk method when the added a axis of symmetry. It's just that was the axis of symmetry that was equal to 0. And then we said it could be any axis of symmetry. Well, now we've just added one more little thing. What if we do 2 disks at the same time? So we're not really taking big giant steps forward. It's just little bits. All right, so let's try one of these so we can actually kind of really just see how this whole thing plays out. And we'll talk more about this in class. All right, it says determine the volume of the solid formed when the region bounded by y equals x and y equals negative x squared plus 4x is revolved around, the first part will be the line y equals -3. And the second will be when it's revolved around the line y equals 9. So first of all, let me just draw a real quick picture so we can see kind of what's going on here, and then we'll take a try at actually figuring out this whole thing. So we have some sort of graph. We have the equation y equals x. So we have this equation y equals x. I mean, I could have gone into the other one, but I'm not going to. And then I have the parabola y equals negative x squared plus 4x. So you can kind of see where that area is, that value that we're determining. So we're dealing with this region between here and here. So part A said we're going to revolve it around the line y equals -3. So we're going to revolve it around the line y equals -3. Now, if you notice that line, if I start from that axis and I go up, the function, the bounded region is greater. So this is going to be a function minus axis one. But the very first one I reach is going to be the blue one. So that'll be the smaller volume. In the red, the parabola will be the larger volume. There's a way to figure out which one is the larger one, and I'll show you that in a second. But you got to make sure you know which one's larger. But notice what happens when I use y equals 9. Notice the functions are going to flip-flop. So now this one's going to be axis minus function, and when I come down from it, I hit the red function first. So that'll be the smaller volume, and the blue will be the greater volume. So not just am I flipping axis minus function, I'm flipping the order of subtracting axis and function, but I'm also going to flip the order of which function it goes first. We'll see that here. Like I said, we'll see that in a second. So first thing we're going to have to do, though, is we're going to have to figure out where this thing's bounded from. So we're going to take our two equations, we're going to set them equal to each other and figure out where our bounds are. So we plug them in here real quick. So I have x squared minus 3x equals 0. Factor out our x. So this thing is going to be bounded from 0 to 3. So when I deal with my volumes here, around the line y equals -3, it's below, so pi goes first, from 0 to 1. We're just going to write the expression. We're not going to actually find the integral of it. We're just going to write the expression. So I'm going from 0 to 3 because those were my bounds were. All right, we're just going to write but not solve. We've already solved quite a bit. I already know you guys can solve these. So we're going to go the greater function minus the lesser function. So the greater function, that was the parabola. So negative x squared. But I have to subtract my axis from it. So minus a -3. And then I'm going to subtract the blue function next. So x minus a -3. So the question that sometimes comes up is, well, how do you know which one goes first? Well, if I combine my function with my axis, I get y equals -x squared plus 4x plus 3. And the other one would have x plus 3. So if I were to take the two functions and have combined them with the axis of symmetry, and then you just pick a number in between your bounds, like for instance, x equals 1. Pick a number in between your bounds, doesn't matter what it is, and then evaluate it for each of those. So if I plug -1 in for this, or if I plug 1 in for this one, I would end up with 6. If I plug it in for this one, I get 4. Well, 6 is greater than 4, so therefore this one right here is the one that's going to come first. All right, let's try the last one, and then we get to call it a day here. What if I plug in my volume on the other one? So volume equals pi from 0 to 3. Now, we said this one, the blue one is the greater one, but the axis is greater than both. So I'm going to go axis minus my furthest function, so 9 minus x, minus 9 minus -x squared plus 4x. And then we are going to go ahead and do our difference quotient, or our two disk methods, and we'll figure out the volume. And again, how do we know that 9 minus x is the greater one? Well, again, if we were to have made both these a functions with the axis, I would have had 9 minus x. And if I were to take the other one, so without graphing it, just take your two functions. So plus x squared minus 4x. and then pick a number in between them to plug them in to see which one gives you the larger value. So, let's see here. If we plug in x equals 1 into the first one, 9 minus 1, that would be 8. If I plug in x equals 1 into the second one, I get 9 plus 1 is 10, minus 4 is 6. Well, this one is the larger one, so therefore it came first. All right, folks. So, recap. Find the disk. It's either going to be the function minus axis or axis minus function, and then you square it. Make sure there's always a pi on the outside of your integral. Now, when I do the washer method, that's basically taking two disk methods and subtracting them from each other. Make sure you do the bigger volume first, and then subtract the smaller volume from it. So, we'll talk more about this in class. Good luck, and I'll see you in the morning.